Presentation in Unit 2, it's entitled Push Your Limits, says I can calculate the motion of heavenly bodies but not the madness of people by Isaac Newton. So the first thing that we need to look at is for our goals is you need to understand the relationship between mass and weight, and we explored that real briefly in the last presentation. We're going to formalize that a little bit, and then you should be able to conceptually and mathematically apply Newton's second law, which is shown in the equation below. So, what we already know. We know that a force is a push or pull on an object, and we know that free body diagrams are used to illustrate all of the forces acting on the object. We also explored the concept of a net force and the net force resulting in a change in motion. Now, we talked about we talked about mass being measured in kilograms. And we also said that weight was measured in newtons. That was nothing new. But whenever we took those for the same object and we found the weight and the mass of every object, we got a graph, and that graph gave us a slope of 9.8. That 9.8 told us that that was the acceleration due to gravity in meters per second squared. So that right there was some useful information because we saw that mass and weight are always related by that same value. So just as a brief review, we know that mass is a measurement of inertia or resistance to change in motion. Remember, it's the amount of stuff that an object has. That it's measured in kilograms, and it's measured using either an electronic or a triple beam balance. We know that weight is a gravitational force. It's not mass. Mass and weight are not the same fundamental quantity. The gravitational force depends on the mass of both objects. Since everything that we tend to look at tends to be measured on Earth, that's usually a constant. So a lot of times we think that mass and weight are the same, but they're not. We also know that all forces are measured in newtons. Okay. Next, we know that the weight on Earth. So weight on Earth is a constant. The distance between Earth and objects is relatively constant. So mass is proportional to weight. So as mass increases, weight increases. So if you double the mass, you double the weight. So they're directly proportional is what we refer to that as. Now, the equation that we have for weight is oftentimes put as Fg is equal to mg, where you have the gravitational force. Remember, anytime that you see an F, the F is referring to the fact that it's a force. The G is referring to the fact that this thing is a gravitational force. On the other side, we have equals m, which stands for mass, and then you have a g. Now notice this g is not a subscript. It's not something that's lower that's used to define the f. This is a variable on its own. It's mg. So in this particular case, the g is referring to the number 9.8 meters per second squared, which is the acceleration due to gravity on planet Earth. Now, if you're not on Earth, you can't use that number 9.8, but everything that we do in this class should be on Earth. Now, this question says, which of these followings are considered to be constants and which are variables? So the first one is weight and mass are considered to be variables because you can change the mass and the weight will change as a result. In this particular formula, we're going to say that g is a constant because we're going to assume that it's on Earth. Okay, now if we change that assumption, we can say that this g is a variable as well, but everything that we deal with is going to be on Earth. So what are the units for each variable in the equation? For Fg, it's a force, so force is measured in newtons. On the other side, you have mass, which is measured in kilograms, and then the last one is g is an acceleration, which is measured in meters per second squared. So those are the units for each one of those. Next, it says the mass of an empty box doubles when filled with newspaper. How does the weight of the empty box compare to the weight of the filled box? So remember, weight and mass are directly proportional. So if you were to double this, this doubles. If you were to triple this, this triples. If somehow this was increased by 5, this is increased by 5 because this g term is a constant. So because of that, if the weight of the empty box is going to be, the weight of the filled box is going to be twice as much, just like it is for the mass. Next it says, what is the weight in standard units of a 50 kilogram student? So if we were to look right here, we're going to say, I'm trying to find the weight, which is Fg. I know that the formula that I have is Fg equals mg. So I need to go ahead and figure out what the values of m and g are. Remember, m is going to be a mass, which is 50 kilograms. G is going to be 9.8 because we're going to assume that the student is on Earth because that's where all students are at this point. You're going to say equals 50 times 9.8. You get out your calculator and you can take out 50 and multiply it by 9.8. And when you do that, you get 490 newtons, which is going to be our answer for what is the weight of this particular student. The mastery level question says the Mars Curiosity rover has a weight of 8810 on Earth. What is the mass on Mars where gravity is 3.71? This is kind of a trick question. And so the reason why is you're given the weight on Earth and you're given the gravity on Mars. So now remember, when you're given the weight on Earth, you need to go ahead and use that value. So the equation that I have is going to be Fg equals mg. Now, if I were to go ahead and say, okay, I have the weight on Earth equals this times the mass and then 9.8. That's the acceleration due to gravity on Earth. Whenever you do this, you can go ahead and solve for the mass. Divide both sides by 9.8. And when you do that, you get the mass on Earth to be about 899 kilograms. Now, at this point, you might say, well, yeah, that's the mass on Earth, but what's the mass on Mars? How am I going to take this gravity into play? Remember, mass is an intrinsic property. It doesn't depend on where you are. So the fact that it's 899 kilograms is on Earth, is on Mars, is in space, is on the sun, is everywhere. It's always 899 kilograms. What changes based on location is the weight. Now, if I would have asked you for the weight on Mars, you would have taken this 899 kilograms and multiplied it by the 3.71. But it was not necessary in this particular example. So now we come to Newton's second law. Now, the relationship between mass and weight is one example of Newton's second law. Newton's second law says that force is directly proportional to acceleration. So if you double the force that's exerted on an object, you double the acceleration. If you half the force, you half the acceleration. If you multiply the force by 100 million, the acceleration increases by 100 million. So as the force increases, the acceleration increases. The second part of Newton's second law says that mass is inversely proportional to acceleration. What that means is, as mass increases, acceleration decreases. So if you were to triple the mass, you would decrease the acceleration to 1/3 of its value. If you were to double the mass, you would half the acceleration, and so on. So whatever you do to the mass, okay, so let's say I increase the mass by a factor of 10. If the mass is up by 10, then what you would do to the acceleration is you would be 1/10 the original value. So it's inversely proportional. That's why it's 1 over that number. So now you come to Newton's second law, and this is the actual equation form of this. Newton was able to take all of these observations and derive the equation F net equals ma. Now you should be familiar with the concept of net force by now, where it's the sum of all the forces, or the combinations of all the forces acting on the objects. It's the combination of all the forces that results in the acceleration. Mass and acceleration you should be familiar with already. So let's look at some examples. The first one says you have a 200 Newton force exerted on two objects below, which will have the greatest acceleration. So remember, the equation is F net is equal to mass times acceleration. So now I have a set value for the force. So I'm going to go ahead and say that this right here is a constant. And you can plug in 200 if you want, but it's got to be the same value. So if I want to have a great acceleration, I have mass and acceleration. So it means the bigger the mass, the smaller the acceleration. The smaller the mass, the bigger the acceleration. Now, if you were to look at these two objects, this refrigerator right here clearly has more mass. So because of that, its acceleration is going to be smaller. So this right here is going to have the greatest acceleration, the styrofoam cooler, assuming that 200 newtons of force is exerted on it. The next one says, what force does a worker exert on a 50 kilogram box if it accelerates at 2 meters per second squared? So what we do is we say, what force? We circle what we're looking for. We underline our numbers. And we say, okay, force is what I'm looking for. Mass is equal to 50 kilograms. Acceleration is equal to 2 meters per second squared. That's my given and unknown information. Now I take my equation and I plug in. Now, one thing that you should realize is this is not just the force the worker is exerting. What it represents is the net force. Now, we're assuming that all the other forces are in equilibrium, but what this refers to is the net force. So I can say F net is equal to 50 times 2. At this point, you can go ahead and solve and say 50 times 2 is 100 newtons. And that represents the force that's exerted by the worker. In the next one, it says a 1,000 kilogram car is towed with a chain capable of exerting a force of 4,000 newtons without braking. What is the maximum acceleration of the car capable of without breaking the chain? So in this case, I have a 1,000 kilogram car. I have 4,000 newtons, and I want to know what the acceleration is. So in this case, I would say F, M, and A. I'm trying to solve for the acceleration in this case. I know the force is 4,000 newtons. Oh, forgot a zero. I know that the mass is 1,000 kilograms. I could use the equation F equals ma. And at this point, I would need to plug in my numbers. And I would say 4,000 equals 1,000 a. At this point, you would divide both sides by 1,000. And when you do that, you end up with an acceleration of 4 meters per second squared. The next example says determine the mass of this particular object. So if you look, this is a pretty tricky graph, and the reason why is you have force down here and you have acceleration down here. So what you can actually do is you can actually solve for the slope of this particular graph. But if you were to solve for the slope of this particular graph, it would be given an a divided by f. Well, if you look at our equation F equals ma, in order to solve for the mass, you would need to get F divided by A, not M divided by, you get F divided by A, not A divided by F. So in order to do this, in order to solve for this, you need to find what's called the inverse of the slope. So instead of taking rise over run, you do run over rise. So I take a look and I say, I start at 0, 0. I pick a nice neat point right there, which is 20 and 5. I say my run is 20. My rise is 5, so that ends up being 4, which gives me 4 kilograms. The last example that we have here says, what is the final velocity of a 1,000 kilogram car initially at rest, in which the engine exerts 500 newtons of force for 12 seconds. Now, this is a mastery level question because it requires us to know information from the previous unit. So it says, what is the final velocity? That's what I'm trying to solve for. Of a 1,000 kilogram car initially at rest, in which the engine exerts 500 newtons of force for 12 seconds. Okay, so you have a mass of 1,000 kilograms. You have an initial velocity of 0. You have a force of 500 newtons. And you have a time of 12 seconds. So now eventually what you want to solve for is the final velocity. But in order to do so, we're going to have to use the equation A equals VF minus VI over T. That's our equation that we have that we can solve for the final velocity. The problem is I do have the time, I do have the initial velocity, but I'm missing this acceleration term right here. So in order to solve for what I want to solve for, I need to know what the acceleration is. Luckily, I have an equation that I've used in this unit that's force equals mass times acceleration. If you look, you have the force and you have the mass, so you can actually plug in. You can say 500 equals 1,000 A. Divide both sides by 1,000, and when you do that, you get A is equal to 0.5 meters per second squared. Now that's really good because now that was the one thing that was missing from this equation over here. So now I'm going to cross back to my original equation, and I can say 0.5 equals VF minus 0 over 12. So at this point, you would look at it and say, okay, well, VF minus 0 is going to be VF. That's going to cancel out. And in order to solve for VF, I just multiply both sides by 12. When you multiply both sides by 12, you end up getting a value of about 6 meters per second.